Continuing from our previous session, we know that a classical model of finding probability can be applied when all the events are mutually exclusive. We wrote it as ME. Then it needs to be exhaustive, and all the events needs to be equally likely, right? Equally likely. In this case, what is the probability of finding of an event, right? So we call that in that kind of experiments. Let's find the probable favorable condition, favorable outputs, and divide it by. So we define the probability of an event A, that is PA, is nothing but MA by, let's say, A, where MA is the number of favorable events, and A is the total number of events, or you can say number of favorable ways and total number of ways of by counting, right? So this classical model will primarily use the counting principles, and we will see how. So let's get started with a few of the basic example. So let's say we have a pair dice, a pair coin. So what is probability? So I'll go slow here with very basic examples, and we will simply move to the tougher questions later on. Probability of getting head, right? So when you fair coin is tossed, of course. So when a fair coin is tossed, there could be two events which are getting head or tail, right? So these are the two events. The total number of events is here 2. So there are two ways of getting an output. And when it says getting head, so there is only one way of getting head, right? So the probability of getting head is nothing but 1 divided by 2, right? There are few more things which is quite important here. Please note the probability of any event, or probability of getting in any head or tail, or let's say any event, it cannot be, should be less than, greater than, equal to 1, right? So in case you are getting a probability of a particular event more than 1, let's say 4, then you have done something wrong, right? So let's try to look another example, the basic example. So if you roll a dice, with 6 numbers, 1, 2, 3, 4, 5, 6. What is the probability that even number appears, right? So let's so again, when you roll a dice, the total number of ways you can get total output you can get is either 1, 2, 3, 4, 5, 6. So there are 6 ways, and then the number of ways you will get an even number appears among 6 numbers will be 2, 4, 6. The favorable output, or you can say F output, is 3 ways, right? So the probability of getting an even number, so we defined that this set as A, is nothing but 3 by 6. Now let's take another basic example. So if you flip a if you toss 2 coins, so if you toss 2 coins, 2 coins are tossed. So fair coins, of course, right, are tossed. What is the probability? Is the probability of getting at least one head, right? So if you write all the possible outcomes, you will get with 4 events, right? And then you can get, this is the first coin output, this is the second coin output. So the total number of ways you can get the output is 4, and you get at least one head here, here and here. So the total number of ways of getting at least one head is 3. So the probability of that will be 3 by 4, right? Now let's take some of the examples from our counting principle. Okay, so okay. Now let's take a look at this one, right? So this is our first example which we will be taking here. So it says 3 identical dice are rolled. 3 identical dice are rolled. The probability that same number will appear on each of them is, okay. So when 3 dice are rolled, using the counting principle, you can find the number of outcomes, right? So there are 3 dice, so each dice will be one place. So number of outcomes for first dice could be 6 ways, that is 1, 2, 3, 4, 5, 6, right? The number of outcomes for the second is also 6 ways, and the number of outcomes for the third dice is also 6 ways. So by multiplication principle, we see that there could be 216 ways of getting output, right? Of getting that output. Okay. Now, if we have to find the probability that the same number will appear on each of them. So this can be, again by the counting principle, you can see there is only one possibility, there are only 6 possibility that this kind of number appear on all the 3 dices, right? 3, 3, 3, 4, 4, 4, 5, 5, 5, and 6, 6, 6, right? So these are 6 ways, and total number of ways is 216 ways. So the probability will be 6 by 216, that is 1 by 36. Okay. So it's easy, right? Let's try to move few more examples. Okay, now let's see. Yes. Okay. So the next example which I'll be discussing here is again a simple one, of wherein you will find the total number of outcomes, and then simply, what you do is that find the favorable outcomes, and then you simply, divide it, right? That's our method, right? Let's try to reduce the font size because it's getting too big. Okay, so three of the 6 vertices of a regular polygon are chosen at random. The probability that the triangle with 3 vertices are equilateral. So let's draw a regular polygon here. It's not up to scale, but you can see that. So these are the 6 vertices, right? So let's say A, B, C, D, E. So how many triangles you can form from these 6 vertices? So from our counting principles, we have learned that it is nothing but finding the combination of 3 from 6, right? Because you can choose this 3, you can choose this 3, you can choose this 3, and it will always form a triangle, right? Triangle, right? So for example, if we choose AFD, then the triangle which will form will be AFD. Similarly, you can choose any 3. So that could be done via 6C3 ways, which is again nothing but 6 into 5 into 4 divided by factorial 3, which is 2 into 1. So all these 3 gets cut. So these are the 20 ways, right? Now, let's try to look what are the possible ways if the vertices are chosen and the triangles are equilateral, right? So we draw this hexagon. So this is again our hexagon. So equilateral means all the sides are equal. So if you have chosen AFD, then you can see that this side is smaller, right? So the only possibility you can do is either this, right? Or you can no, I think yes, and or you can do via this. So there are 2 other ways the equilateral triangle can be formed. So either you choose these alternative sides and these alternative sides. So there are only 2 ways of forming an equilateral triangle. So henceforth the probability will be nothing but 2 by 20, which is 1 by 10, right? So this is another example. Okay. Now let's see a few more examples to understand it more and more. Okay. Now let's take simple example. Okay. Not the tough ones. We'll keep the tough ones for the later part. So the urn has with 3 white balls and 4 black balls. If 2 balls are drawn simultaneously, what is the probability that both balls will be white? So in total we have around 7 balls, and out of which 3 balls are drawn simultaneously, meaning by 3 balls are chosen. 3 balls are chosen. Okay, so the total number of ways that can be done is 7C3, which is nothing but 7 into 6 into 5 divided by factorial 3, which is 6. So that is 35 ways, right? What is the probability that the both balls are white? Okay, so we have 3 balls, 3 white balls, and if the both balls, okay, if 2 balls are chosen, okay, sorry, not 3 balls. So we'll just remove this part. Okay, so 2 balls needs to be chosen, not the 3 balls. Okay, so 2 balls needs to be chosen, balls to be selected. Okay, to be selected or chosen. So that can be done by a 7C2 way, which is nothing but 7 into 6 divided by factorial 2. So that is 21 ways, right? So what and then what is the probability that both balls will be white? So you have to now select from 3 white balls. If we have to select 2 balls such that both are white, so the number of favorable cases will be selecting 2 balls out of 3 balls, right? Or choosing 2 balls out of 3 balls. So that will be nothing but 3C2. So that will be again 3 into 2 divided by, so that is 3. So the probability of getting 2 white balls in 2 selection will be 3 by 21, which is 1 by 7. Okay. So let's take a look at similar kind of example. So the urn with 3 white balls and 4 black balls are again the same. The condition remains the same, but we'll try to find the probability of something else. So we have the urn again with the 3 white balls and 4 black balls. Now this time 3 balls are taken simultaneously. What is the probability that 2 of them are black and 1 is white? Okay. So the total number of ways 3 balls can be selected from 7 balls is again nothing but 7C3. So your total outcome is now 7 into 6 into 5 divided by factorial 3, which is 6. So these are 35 ways. Now if you have to select 2 of them are black, so how many ways that can be selected? That can be selected in 4C2 ways, and 1 is white, so that can be selected in this way. So this is nothing but 4 into 3 divided by 2, which is 6 plus into 3. So that can be done by 18 ways. So the probability of this thing will be nothing but 18 divided by 35, right? In the last sessions, we have given various examples. We have tried to solve the various classical model problems. Now, finally, in this session, we will be taking a few more problems and try to solve using the classical models. So this will be quite a little bit trickier problems. So let's see how we can do that. If the letters of the word attaching are written down at random in a row, find the probability that no two S occur together. So first we see that there are 8 places, right? 2, 3, 4, 5, 6, 7, 8. Yeah, and we have to arrange these 8 numbers or letters where there are 2 A's, 4 S, and 1 I, and 1 N, right? So this can be arranged among themselves in a total number of ways. This can be arranged. So it's like arranging 8 letters in 8 of places where 2 are of similar kind, 4 are of similar kind. So that is nothing but factorial 8 divided by factorial 2 into factorial 4, right? So that so we leave it here that these are the total number of ways. number of ways, right? Now let's try to find the probability for that no two s occur together. So if you put you here a I and n. So what we'll do here is again from the counting principle, the way we used to count. So what we can do is that we can put I, n into four places. So let's say we put here a, then we put a, for example, then this I and this n, right? So we can put the four S's into these five places, right? So that can be, done via 5C4 ways, right? And again, which is nothing but, 5. And again, these four letters can be arranged among themselves in factorial 4 by factorial 2 ways, right? So now we compute the final probability of it. So we find that the final probability is nothing but 5 into 4 divided by factorial 2, and this whole divided by factorial 8 divided by factorial 2 into factorial 4, right? So that is nothing but 5 into 24 divided by 2, which is 60 divided by, this is factorial 8, so factorial 4 can be cut, so it will be left with 8 into 7 into 6 into 5 divided by factorial 2, that is 2. So this is nothing but 60 by 8, 40, and that comes out to be 1 by 14, right? So this is one of the problems where you have found the probability using the typical methods which we have used in the counting principle, right? Now let's take the one more example. So we have this one is done. Okay, now let's take this one example. So we have this case now that four dices, fair dices D1, D2, D4, each having 6 face number 1, 2, 3, 6, 4 are rolled simultaneously. Find the probability that D4 shows a number appearing on one of D1, D2 or D3, right? So first we compute the total number of ways again. So there are 4 dices. So it says that there are 4 places and each dice has an outcome of 6. Similarly, this will have 6, this will have 6. So that will be by multiplication principle. The total number of outcome will be 6 to the power 4, right? So we write it total number of outcome is 6 to the power 4, right? Now, let's try to subdivide this problem of finding that D4 shows the number which are appearing on one of D1 and D2 or D3. So first we consider that, first we understand that, any number on D4 can come in a 6 ways. So it could be 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, right? So the first assumption is that the number of ways of any number coming in D4. So number of outcomes for D4 is 6 ways, right? Now we see that we can say that only in one of D1, D2 or D3 the same number appears. So let's say the number 1 appears on D4, right? So there are 6 ways, please note, yeah. So 2, 3, 4, 5, 6 can come. Now among one of them of D1, D2 and D3, this one has appeared. So either here or here, only one place, right? So this means that how many ways this can be arranged. So first we have to select a 1 out of 3, so that can be done into 3C1, that is 3 ways, right? So in one of the cases this one has appeared, that is 1. Now the rest of the D2, so let's say it appears in D2, the same number 1. Now D1 and D3 have 5 possibilities left each, so that is nothing but 5 into 5, right? Now and the total number of ways the outcome can come from D4 is 6. So this is the case 1, when then only one of D1, D2, D3 contains the number of D4, right? Similarly, the second case will be 2 of D2, D1, D2, D3 contains the number of D4, has same number as D4, right? So again, there are 6 ways for getting output of D4. Selecting 2 out of this, so we'll get 3C2, which is again 3, right? And then only 1 is left because 2 of them have the same number. So let's say 1, 1. Again, if D1 has a 1. So we are left with the 5 options for D2, right? Because it means it can't be 1, right? So we are left with the 5 options. So that is nothing but 6 into 3 into 5, right? And finally, we will see when all the 3 D1, all 3 D1, all of the 3 D1, D2 and D3 will have the same number as D4, right? So D4 is 1, then all these 3 are 1, right? So this can be arranged into 6 into, there is only one way, so this is 6 into 1, right? 6. Now, so our final outcome will be, adding these 3 and dividing by the total outcome, right? So that we'll see here as 6 into 3 into 5 into 5 plus 6 into 3 into 5 plus 6 into 1 divided by total number of ways, so that is 6.4. So we take 6 common here and cut it, so it will be left with 216 ways. So this is 75, 15 plus 1, so that is 19 by 260 ways, right? So you can see that the various problems in probability comes in a way that you will need to do the actual counting work and then you finally decide, so what is the probability of it. These are the few of the examples which I would like to add in the classical model. From the next sessions, we'll be entering into the section called the set theoretic approach of solving the probability problem. That is the most of the part of the probability, and we will use all our set theory knowledge there. Thanks for watching this video. If you want to see such more videos, subscribe our channel or visit our website www.deepdivemaths.com.